All right, on Thursday we started talking about centripetal acceleration and centripetal force. We know that in uniform circular motion, an object is moving in a circle at a constant speed. If it's going at a constant speed, okay, clearly not speeding up, not slowing down, how do we have an acceleration? How can we talk about an acceleration and a force when we're not speeding up or slowing down? It's changing direction, right. Velocity is a vector, and acceleration is defined as the rate of change of velocity. So since velocity is a vector and we're changing velocity, or we're changing direction, then we're also changing velocity. That therefore has to be an acceleration and a force. But we're not going to find the acceleration by the equation that we learned way back in Unit 1. It's still technically applicable. It's not really going to help us very much when we're dealing with objects moving in a circle. Rather, for acceleration, we're going to use this equation. A is equal to v squared over r. What does v stand for? What does v stand for there, please? Brennan? Good, it's speed, not velocity, because the velocity is changing. The speed isn't. Okay, we're going to put in the speed there, not the direction, just the speed. R stands for the radius of the circle, right? And it's going to be measured in meters. The centripetal acceleration that we get here has a direction associated with it, but this equation isn't going to tell us what the direction is. It's just going to give us the magnitude of it, hence the absolute value signs around A. How are we going to get the direction? If the equation doesn't tell us the direction, how do we know the direction of the centripetal acceleration? I'll give you a hint. It's easy. What's the direction of the centripetal acceleration? Always. Right? It's toward the center of the circle. So if the object is right here, the acceleration is inward. If the object is right here, the acceleration is inward, and so on and so on. The acceleration is always directed toward the center of the circle. So the equation won't tell us what the direction is, but that's okay, because we can always find the direction by looking at which way the center of the circle is. The other equation that we learned on Thursday was centripetal force. It looked real similar to centripetal acceleration. It said F is equal to m times v squared over r. In other words, m times a, m times the centripetal acceleration. The centripetal force is also directed toward the center of the circle. We're not going to get that direction from the equation. That's okay, because we can get it from the definition. Centripetal means center seeking toward the center of the circle. All right. What are the units for centripetal acceleration? You guys all know this, right? What are the units for centripetal acceleration? Sure you do. What are the units for acceleration? What are the units for acceleration? Okay, meters per second squared. What are the units for centripetal acceleration, Nick? Meters per second squared. Okay, it's still an acceleration, right? What are the units for centripetal force? Okay, what are the units for centripetal force? What are the units for force? Newtons. What are the units for centripetal force? Newtons. Good. Okay, it's no different. Okay, we call it something different, centripetal acceleration, centripetal force, but the units are still the same as they always have been for acceleration and for force. All right, we had 3 bits of homework last night, 255, 256, and 259. 255, somebody already asked me to go over question number 3. We'll take a look at that now. It says the helicopter blade has a diameter of 14 meters and a centripetal acceleration of 25, 27. What's the period of the helicopter blade? That's a good question, actually. Okay, that's a good question. Let's write down some givens here. For number 3, my diameter is 14 meters. That means my radius is what? 7 meters. Good. My acceleration, we're given as 2527.0 meters per second squared. We're looking for the period. We're looking for big T, the time that it takes for one revolution. You can take a pretty good guess that this is going to be a really, really small number. Okay, if it's rotating with an acceleration of 2,500 meters per second squared, it must be going pretty quick. And if it's going pretty quick, then it's not going to take very long for this helicopter blade to go around once. Now, how are we going to find T? There's only one equation involvement. Well, I shouldn't say that. There's a couple. T is equal to the number of, the time per number of revolutions. That's not going to help us because we don't know what the time is or the number of revolutions. We also know that v is equal to 2 pi r over t, and t is therefore equal to 2 pi r over v. We don't know what v is, but we can find v by using my centripetal acceleration. Right, Lane? We know that a is equal to v squared over r. Let's solve for v. The r goes up by multiplying, and we square root the v squared to get v. Now, we're going to say v is the square root of 2,527 times r. What was r? 7 meters. Let's square root that to get v, and then now that we have v, let's plug that back in there to get t. When we do the math there, it should work out to be 0.331 seconds. We predicted a pretty small time. Did we get a small time? Yeah, so in other words, it makes 3 revolutions in 1 second. It makes 1 entire revolution in a third of a second there. Yeah. Yeah, yep, yeah, you're right. Is that good? Who asked me for that question? Brendan, is that okay? All right, let's take a look at 256. Any issues with question 1 or 2 on 256? Number 2. A 0.0021 kilogram pebble was stuck in the treads of a dirt bike's wheel. The radius of the wheel is 23 centimeters, which we're going to want to convert that to meters, right? Centripetal force, what's the speed of the wheel? Let's write down our givens here. Mass is 0.0021 kilograms. We know that the radius is 0.230 meters. The force is 0.660 newtons. We want to find speed here. So we're going to take our equation. I think it's pretty obvious which equation we're going to use here, mv squared over r. We're going to take that and rearrange it to solve for v. The r goes up by multiplying. The m goes down by dividing. And the square disappears by, what are you going to do with that to get rid of the square? Yeah, I'm going to square root it. So it becomes square root of f times r over m. So v is equal to, what do we get here, 0.660 times 0.230 divided by 0.0021. Get a number for that. Press equals on your calculator. Get a number for that. Then square root it. And when we do that, we should get 8.5 meters per second. Amelia, is that okay? Was it a conversion issue there? Or was it rearranging? Okay. Don't forget, we've always got to be in those base units. Ever since the first day of class in Physics 20, we've wanted meters, right? Meters, seconds, and so meters per second squared, and so on. All right, finally, we had page 259. Any issues with the questions on page 259? Yep. Number 2. Is that it? K2 it is. Number 1. Number 1 says an Edmonton Oilers hockey player, mass of 100 kilograms, carves a turn with a radius of 7.17 meters while skating and feels his skates begin to slip on the ice. What's the speed if the coefficient of static friction is 0.80? So what's happening here is that he's beginning to go too fast, right? He's going around this turn. He feels his skates beginning to slip. He's feeling his skates beginning to slip because he's exceeding the maximum possible force of static friction. Sideways, his skates aren't moving, right? So it's static friction, sideways. But as they start to move, we've just barely exceeded the maximum force of static friction. So what are we going to do here to find that coefficient, to find the maximum speed that he's going here? Let's write down his givens. 100 kilograms is his mass. The radius is 7.17 meters. Coefficient of friction is 0.80. Looking for speed here. We know the centripetal force is equal to mv squared over r, but that's not enough to give us v. because we don't know what F is. What is it that's causing centripetal force? Remember on Thursday we talked about how centripetal force is not fundamental. It's always caused by something else. The keys go around my head. It's caused by the string. The earth goes around the sun. It's caused by gravity. A car goes around a turn. It's caused by friction. What causes the force of friction here? What causes the force of friction here? What causes the centripetal force here? Eric, you know the answer to this question, right? What causes the centripetal force here? Good. Thank you, Bo. It's friction. So if friction causes the centripetal force, then we're going to set friction equal to the centripetal force. We can say mv squared over r is equal to mu times m times g, right? The normal force being mg in this case. Now, if you want to just solve for ff and then set it equal, that's okay too. Doesn't really matter whether you set them equal right now or solve for ff and then set them equal. Bottom line is they're equal to each other, so set them equal at some point. Now, masses cancel here, so we don't actually need to know that the mass of the hockey player is 100 kilograms, although if you put it in, it'll still give you the right answer. We're looking for v here. So the r goes up by multiplying. The square disappears by square rooting. It becomes the square root of 0.80 times 9.81 times 7.17 meters. We get a speed there, presumably 7.5 meters per second. Make sense? Is that okay? Let's take a look at number 2 now. 2 says automotive manufacturers test the handling ability of a new car design by driving a prototype on a test track in a large circle at ever-increasing speeds until the car begins to skid. A prototype car with a mass of 1,200 kilograms is tested and found to skid at a speed of 95 kilometers per hour, which we're going to want to convert that to meters per second, right? We want to find the coefficient of friction between the car tires and the track. Let's first convert that to meters per second. 95,000 meters divided by 3,600 seconds. What does that give me? 95,000 divided by 3,600, right? 1,000 meters in a kilometer, 3,600 seconds in an hour. 26.388 meters per second. Thank you, Brandon. Now, we're going to do the same thing here basically as you did in question number 1. The centripetal force is what keeps it going in a circle, but it's got to be caused by something, and clearly in this case it's going to be caused by friction. So we're going to say FC is equal to FF, or we're going to say mv squared over r is equal to mu times m times g. M's cancel, although we don't have to cancel them. We've got the mass here. We can plug in the value of the mass if we want. But we can save ourselves the bother of plugging it into an equation if we cancel it out. Oh, sorry, we're looking for mu this time, aren't we? So we got to take the g over by dividing. It's going to be mu is equal to v squared over r times g. 26.388 squared divided by 100 times 9.81. That should give us, when we do that math, 0.710. When you see that number, does it seem like a reasonable number? If you get 57, well, that's not reasonable, right? If you get 0.71, that seems very reasonable. Coefficients of friction are usually in that 0 to 1 range. It just seems pretty reasonable. All right, you good at that? Any issues? Okay. I want to talk just for a couple minutes on the difference between 2 types of forces that you've undoubtedly heard of before, but probably not really thought about in terms of what's what or what the difference is or even what they necessarily mean. Centripetal force, that's the one we've talked about so far. Okay, that is the force that acts toward the center of a circle. The force on every object that's moving in a circle acting toward the center of the circle. The centrifugal force, and notice I've got that in quotation marks. I'll tell you why in just a second. It's the force, I'm also going to put that in quotation marks, that pushes it out. It pushes an object out toward the outside of the circle. When you're going around a turn in your car, and you're going around that turn fairly fast, you feel yourself being pushed against the car door, right? When you're on that Gravitron ride at the Stampede, you're being pushed against the wall, and you're sticking against the wall. When you're on that, I forget what they call it at Callaway Park, the one that spins around and you kind of get pinned against the wall. You guys know which one I'm talking about? Okay. It's the centrifugal force that's pushing you out. The problem is the centrifugal force doesn't really exist. There's really no such thing. So how are you pushed out towards the car door when you're going around a turn, or how are you pushed against the wall of the Gravitron ride or that ride at Callaway Park if you're not really being pushed? How is it that you're stuck against the wall? How is it that you can't lift your head up off the wall of that ride when there's not really any force pushing you out? The centrifugal force is really just what? It's really just inertia. It's really just inertia. I was going to say pushing you in a straight line, but inertia doesn't push you anywhere because it's not a force. It's really just inertia taking you in a straight line. Then the wall pushes you in. So why do you feel like you're being pushed out if it's really just a force that's pushing you in? Inertia taking you in a straight line, and then the wall pushing you in. Well, every time we experience an acceleration, we experience what we call a pseudo force, a fake force, a force that doesn't really exist. Okay, let's assume that I'm sitting at a stop sign in my car, like this, and I get hit from behind. Okay, which way do I accelerate if I get hit from behind? I accelerate forward, right? What does it feel like to me? It feels to me like I'm being pushed back into my seat, right? You're in an airplane. Okay, first time I was in an airplane, I wasn't much younger than you guys are right now. Okay, I've flown hundreds of times since that, but the first time I think I was 14 years old. Yeah, I remember I was flying from Toronto to Halifax. I remember I was by myself flying from Toronto to Halifax. I got on the airplane, I was excited. Okay, we're taxiing out to the runway. Okay, slowly, like you taxi out. Okay, and then you make that turn, and as soon as you get onto the runway, all of a sudden you're going from 0 to several hundred kilometers per hour in a few seconds. You accelerate at a really, really high rate. Okay, you're accelerating forward down the runway. What does it feel like is happening? It feels like you're being pushed back into your seat. Are you being pushed into your seat? No, the seat is pushing you forward. It just feels like you're being pushed back. Whenever you have an acceleration, you feel a pseudo force in the opposite direction. Okay, I accelerate forward, I feel like I'm being pushed backwards. If I accelerate toward the center of the circle, i.e. centripetal, then I feel like I'm being pushed outwards, toward the outside of the circle, right? The centrifugal force. Does that make sense? Doesn't exist. We just feel it because we're really accelerating in the opposite direction. And anytime we have that opposite acceleration, we got a force. It doesn't really exist. That pseudo force that makes us feel like we're being pushed out. Okay, that's the difference between centripetal and centrifugal. Centripetal does exist, always pushes you toward the center of the circle. Centrifugal force doesn't exist. It's just inertia and your centripetal force that's pushing you toward the center, kind of combined, making you think you're being pushed out. All right. Here's your last big topic that we're going to do before your West Edmonton Mall trip, and this is a pretty important one. We're going to analyze now vertical circular motion. And you can imagine where this comes into play tomorrow. We're going around a roller coaster loop. We go upside down in a circle. We're not going horizontal in a circle, although that will happen tomorrow. You go horizontal in a circle. But the biggest portion of this analysis, at least, is going to involve going upside down in a circle. We're going to learn to analyze two spots on that circle. When you're at the top of the circle and when you're at the bottom of the circle. In both cases, you have two forces acting on you. Or the roller coaster car, at least, has two forces acting on it. There is the force of gravity that acts down. In fact, that force of gravity is going to act down in both cases. It doesn't matter where you are or what your orientation is, whether you're right side up or upside down, the force of gravity will act down on you, wherever you are on Earth. There's another force that acts on these cars as well, though. That force is called the, no. Well, yes, but Riker said the centripetal force, and he's right, but I want to talk about something else before I talk about the centripetal force. There's also the normal force, the force of the track pushing on you. Now, if I'm at the bottom of this circle, the track pushes which way on me? Pushes up. So we're going to say the normal force is up there. If I'm at the top of the circle, then the track pushes down. The track pushes down on me. So I'm going to say Fn is downward. Now, at this point, you could probably analyze this yourself without my help. Because we know whenever we see a free body diagram, we did this ad nauseum in the last unit. Whenever we see a free body diagram, we say F net is equal to the sum of the forces. In this case, it's Fg plus Fn. And in this case, it's also Fg plus Fn. We got a difference in direction here, but we get the same basic principle that applies, the same two forces that apply, just in different directions. What do we say in the last unit? Our next step is always F net is equal to the sum of the forces, but it's also equal to what? M times A, right? M times A. In this case, we'll say it's MA again, but A is V squared over R. The type of force that we have is centripetal force. So instead of saying MA, we're going to say it's MV squared over R. It's the same thing, but because we're talking about a centripetal acceleration, we're just going to replace the A with V squared over R. MV squared over R is equal to Fg plus Fn in this case. And the second one, it's the same thing. MV squared over R equals Fg plus Fn. They look exactly the same. So how do we distinguish between the top picture and the bottom picture? Signs. Fg right here will be what? Positive or negative? This one's an easy one, right? Fg is what? You guys better get this here. Fg is negative. Fg in this case is just put up your hands here, please. Fg is what? Krista, which way is Fg in the bottom one? Right. It's downward, so we're going to make it a negative value. What about Fn in the top one? The normal force becomes negative, good. And what about Fn in the bottom one? It's going to be positive, good, because it's acting up toward the center of the circle. Now, the centripetal force, we always said the centripetal force is not a force on its own. It's always caused by something else. In both of these cases, it's actually caused by two forces, not just one. Not just the string as my keys go around my head, or not just gravity as the Earth goes around the sun, but two forces, Fg and Fn. The centripetal force, the net force, acts which way when you're at the top of the circle? Remember, it's always toward the center of the circle. If you're at the top of the circle, then where is the center of the circle relative to you? Devin, which way is the centripetal force when you're at the top here? Yes. Yeah. If you're at the top, where is the center relative to you? Down, below you, right? So this is going to be a negative value when you're at the top. At the bottom of the circle, the centripetal force still has to act toward the center. Where's the center relative to you when you're at the bottom this time, Nick? Yeah, it's going to be up, so it's going to be a positive value. So we got a couple of differences here in terms of signs, but that's it. When we set the equation up, we set it up exactly the same way. When we plug numbers in, that's when we worry about distinguishing them. That's when we worry about what's positive and what's negative. Okay? So set it up the same every time, whether you're dealing with the top or the bottom of the circle. But when you plug numbers in, make sure you take into account whether those numbers should be positive or negative. Here's a problem. 5.7264, it says a bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius of the circle is 0.75 meters and the speed of the bucket is 3 meters per second. What's the tension of the rope in position C as shown in figure 5.31? So what's the tension on the rope right here at position C? The tension on the rope is what variable? Okay, they've called it FT here, but we called it what? In the context of the roller coaster, it's no. Fn, the normal force, right? Fg is gravity pulling it down. Okay, the Fn is the track pushing the roller coaster car up. If we're talking about a bucket of water, what pulls the bucket of water upwards? Well, it's not a track, it's a string, right? It's a tension in the string. It's the same thing. If you want to call it Fn still for the bucket of water, that's fine. Really call it whatever you want. They've drawn a free body diagram for me already. Fg is acting down, Ft is acting up. I'm going to say F net is equal to the sum of the forces, Ft plus Fg, or you could say Fn plus Fg. We're going to say mv squared over r is equal to Ft plus Fg. And we're going to plug in some numbers. M is 1.5 kilograms. V is 3 meters per second. Don't forget to square that. That's probably the most common mistake that people will make here is forgetting to square the V. The radius is 0.75 meters. Ft is what we're looking for. How hard does the rope have to pull to do this? Or if this is a roller coaster problem, how hard does the track have to push up in order to do this? Right, Fraser? Write this down. We add to that m times g, 1.5 times 9.81. But remember, now that we've plugged in numbers, we have to worry about signs now. The centripetal force, mv squared over r, is that positive or negative? Remember, it acts toward the center of the circle. The center of the circle is up relative to where you are. Is that a positive or negative value? Right? Good. So we're going to make that positive. It's positive by default, right? What about gravity? Which way does it act? This one's not rocket science. Gravity acts down, so therefore it's going to be a negative value. Good. Okay, let's do this on our calculator, okay? Let's get the left-hand side here. Let's say 1.5 times 3 squared. Divide that by 0.75. Okay, on the left-hand side, we have 18. Now, let's write that down there. Positive 18 is equal to Ft minus 14.93. Is that right? No, 14.715. Is that right? We're going to take the 14.715 over to the other side by adding, because it's a negative value, it becomes 32.715 newtons. We're going to round that to 3 digits, 32.7 newtons. So the string at the bottom of the circle has to be pulling at 32.7 newtons. Quick question here, though. When you're at the top of the circle, they didn't ask us for this, but when you're at the top of the circle, is the force of tension on the string going to be greater or smaller than it is when you're at the bottom? Bigger or smaller? Why smaller? Yeah, they're both pulling in the same direction. The string doesn't have to pull as hard to keep you in a circle because gravity is helping it. Here, at the bottom of the circle, gravity isn't helping the string. Gravity is acting against the string, right? String's trying to keep it in a circle. Gravity's trying to pull it out of a circle. That makes sense? Okay, let's take a look at question number 1 and 3, please, on page 264. 1 and 3 on page 264. Okay, homework tonight, guys. Finish this up, obviously, 264. Your homework, in addition to that, will be check and reflect questions on page 268, number 1 to 13. Please make sure this stuff is done for Wednesday. Okay, we got our field trip tomorrow. Make sure this is done for Wednesday, please.